Hello and welcome friend. In this new video we will talk about a function of a complex number, limit of a complex number and theorems on a complex number. Friend, you are familiar with the definition of a real valued function. Function is a nothing but a rule that assign to each member of a domain set to a set particular set. If we have two set A and B and a function is defined from A to B, then A is a domain set and B is a codomain set. So function is a relation between these two set A and B, where the relation is defined for every member of A. There is a unique value of the domain codomain set B. So same definition is applied here. We define a function is a rule that assigned to each member of a function. Now here suppose S is a domain set. S is a domain set and we define F is a rule. F is a rule that assign to each Z in S a complex number W. Then so here again we have two set. This is my S, which consists of set of complex number that are Z, and here in another set, suppose that set is a P, which consists of again a complex number. Whenever we assign each member Z to a member W, then such type of relation is called as a function. So here we denote this U by complex number U plus IV, and as usual we denote this Z as X plus IY. So therefore f of Z, or that means f of X plus IY, equal to U plus IV. So this is the value of the function, which is again a complex number. This is in term of coordinate x and y. So u is a function of x and y, and v is also a function of x and y. Now whenever we have z is a function of r and theta, as we know in terms of polar coordinates, these values of u and v are also in terms of r and theta. That means f of r into e raised to I theta is equal to u of r comma theta plus I into v of r comma theta. For example, my function f of z is equal to z square. Then let us find the values of u and v. So friend, we know that what is a z square? We write it is equal to u of x comma y plus I into v of x comma y. Then z square, this is equal to z. Z means what? X plus I y whole square. So we write expanding this x square plus 2x iy plus iy whole square. So this is equal to x square I square y square. I square means minus 1. So this will be x square minus y square plus 2 into I x y. Now let us compare this with this value u of x comma y plus I into v of x comma y. Then you can see that we get here u of x comma y equal to x square minus y square, and here what is v of x comma y equal to 2xy. So this is the function. Now in terms of r and theta, suppose then f of z is equal to r into e raised to I theta whole square. This is equal to r square into uh, r square into e raised to 2 I 2 theta equal to r square into e raised to I theta by using the Euler's rule, cos of 2 theta plus I into sine 2 theta. This is equal to r square cos 2 theta plus I into r square sine 2 theta. Now compare this u of r comma theta plus I into v of r comma theta. So we easily get this is equal to u of r comma theta equal to r square into cos 2 theta, and what is v? My v is v of r comma theta equal to r square sine 2 theta. So friend, you can see that how we easily applied the rule of real numbers to the rule of complex number for defining a function. This is a very important concept in mathematics. Whenever your idea of function is cleared, you can define functions. So this is a very simple example of function. Remember that function is nothing but a rule between the two sets with the condition that to each member of a domain set there is a unique member of the codomain set. Whenever such a type of relation is satisfied, then that relation is called as, that rule is called as a function. Same definition is applied to the set of complex number, and here we have seen a very simple example. Now we define using this definition of a limit, which is a very important definition in mathematics. Limit, remember the definition of limit in a real analysis. So that parallel, we define the parallel definition for the complex number. Friend, whenever y is equal to f of x is a function, then we know that we say that f of x approaches to L whenever as x approaches to C. This is in terms of epsilon and delta definition. Mod of f of x minus L is less than epsilon whenever x minus C is less than delta. This is epsilon delta definition of a real number. So friend, here you can see that instead of y equal to f of z, we have taken w equal to f of z, y equal to f of x. Similar definition, we say that f of z is approaches to w0 whenever this z is approaches to z0. We define the same definition, epsilon delta definition, that is mod of f of z minus w0 is less than epsilon whenever z minus z0 is less than delta. This definition, you can see that instead of f of x we have just taken f of z, and all other symbols here z is used for complex number, and therefore we have taken z instead of x. Okay, so this is the simple definition of a limit, and we write the definition of limit. A function f be defined at all points z in some dilated neighborhood. For neighborhood, I am using this word, short word NBT. This is for neighborhood at z0. The function is said to be a function is said to be have a limit, have a limit as z approaches z0 if for each positive number, or each positive number epsilon, there is a positive number, there is a positive number delta, there is a positive number delta such that this condition mod of f of z minus w0 is less than epsilon whenever mod of z minus z0 is less than delta. Whenever this condition is satisfied, we write in short as f of z, limit of f of z, z tends to z0 is equal to w0. So this is a simple definition of limit as usual in calculus and in real analysis. So friend, when this definition is satisfied, we say that this function have a limit, and that limit is w0. Let us see one example regarding this. Suppose that we have to show that let us take example, show that limit of f of z is equal to I divided by 2 whenever z tends to 1, where what is f of z? F of z is equal to Iz divided by 2. Okay, so we have to show that this this condition mod of f of z minus w0 is less than epsilon, and for this epsilon there exists a delta. So we have to find this value of delta. Whenever this delta is exists depending on the epsilon, then we can say that this limit of f of z is equal to I divided by 2. So here what is need? We need to find this value of delta. That means we have to show that whenever Iz divided by 2 minus limit I divided by 2. Okay, so this is mod, this is my f of z, this is my w0 is less than epsilon. Okay, so we have to show that whenever this is less than epsilon, there must have a delta. So let us first calculate this. This is Iz divided by 2 minus I divided by 2. We can take 2 common, so we write this as a 2. Again we write this as a I into z minus 1, right? So applying the modulus property, this is 1 divided by 2 into mod of I into mod of z minus 1. But friend, what is mod of I? Mod of I is a 1. So 1 by 2 into mod of z minus 1. Right, so this is when z minus z0 is less than delta. We have to find this delta. Here what is z0? Z0 is a 1. Okay, so already we have this term in this expression, so we have to this is therefore mod of Iz divided by 2 minus I divided by 2 is less than epsilon. So when this term will be less than epsilon, whenever this is equal to what? That is 1 divided by 2 into mod of z minus 1. This will be less than epsilon. So obviously when this term will be less than epsilon, this will be less than epsilon. Okay, now you can see that is multiplying by 2, we get that z minus 1 is less than 2 into epsilon, right? So let us take this value, 2 into epsilon is equal to delta. So what we have taken? We have chosen this delta equal to 2 epsilon, right? So we get that we have a delta value whenever Iz divided by 2 minus I divided by 2, this is less than epsilon, whenever this z minus 1 is less than delta. What is delta? Delta is a 2 epsilon. So the condition is satisfied. Look at this, mod of f of z minus w0 is less than epsilon whenever z minus z0 is less than delta. Condition is satisfied, and hence using this we can say that limit of this f of z whenever z tends to 1 is equal to I divided by 2. So we have proved that shown that the limit of f of z is equal to I divided by 2. Now we will prove that this limit is again a unique number. The function do not have more than one limit. Okay, so suppose that limit of f of z tends to z0 equal to, this is w, and if this function f of z, if this is possible, limit of f of z tends to z0 is equal to w0. Now what happen if this? Now applying the definition, see here, for epsilon greater than 0 there exists delta 1. I have taken two limits, so we take 2 delta 1. For the same epsilon we have mod of f of z minus w is a less than epsilon whenever z minus z0 is less than delta 1. Now for this limit and for the same epsilon, suppose there exists a delta 2. That means mod of f of z minus w0 is less than epsilon whenever z minus z0 is less than delta 2. Okay, so this is a point z minus z0. We have taken one circle. This is a circle having the radius delta 1, and this is another circle having radius delta 2. Okay, so let us take the minimum. So here we have taken already in this diagram, delta 1 is a minimum. For all these values, the condition, both conditions are satisfied. Okay, so see the common region. For this common region, these conditions are satisfied. That means if we take, let delta equal to minimum of delta 1 comma delta 2. For this common region, mod of f of z minus w is less than epsilon, and mod of f of z minus w0 is less than epsilon for z minus z0 is less than delta. For these values of z minus z0, for these values of neighborhood, we have taken common region. This is a point z0 center, and we have taken, this is a my delta. For these values of the function z, these values of z, the distance between f of z minus w is less than epsilon and f of z minus w0 is less than epsilon. Okay, so for this region, suppose this condition is satisfied. Now you can see that if we compute the distance between these 2 points w and w0, this is equal to, we write this as a w minus f of z plus f of z minus w0. Okay, addition and subtraction of this. Now let us apply the modulus property. This is equal to w minus f of z plus mod of f of z minus w0. Okay, so by using the modulus property, you can see that this is a less than epsilon, again this is less than epsilon. So what we get, w minus w0 is less than 2 into epsilon. Now friend, what is epsilon? Epsilon is any positive value greater than 0. That means we can choose very small value of this epsilon, and for this small value of epsilon, the condition is satisfied. This positive value is less than this much smaller value. So only possibility is that this is, suppose for larger scale, if we choose 0 0 0 0 0 1, and for this value, this mod of w minus w0 is again less than this, here is my 0. So this is possible only when this is equal to 0. That means w minus w0 equal to 0. 0 is the only value which is smaller than any positive value, any arbitrary value, and therefore this w minus w0 is equal to 0. So this shows that w equal to w0. That means the function have a unique limit. The function do not have a more than one limit. Function cannot have two limit points. Okay. uh, okay, this is the very important point regarding the limit of a function. Now here we see one more theorem regarding this limit point. So first we will show that this function, let us shows that one problem. show that show that the limit of f of z equal to z divided by z bar does not exist at z equal to 0. We have to show that this function, limit of this function do not exist. Okay friends, so we have seen that the function have a unique limit. We use this theorem. The function have a unique limit. Okay. We apply this theorem to prove this. Now friends, we remember the complex plane. Now this is z equal to 0, center of this complex plane or Argand plane. Now this is a imaginary axis, this is imaginary axis, and this is a real axis x, this is y, whenever z is equal to x plus iy. You can see that we can approach z approaches 0 along this line, 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 along this line. So there are number of ways where we this number tends to 0 to 0, tends to 0. Now if this z tends to 0, if my point is on real axis, suppose z approaches 0 along real axis, along x-axis, and we know that on x-axis y point is 0. That means this is x comma 0. In that case this z will be like this, x plus 0 I. Okay. Then f of z equal to, let us see, f of z equal to x plus 0 I divided by its conjugate, x minus 0 I. Now you can see that this is x divided by x and this will be 1. Now whatever may be the value, this is a constant sum, so limit of f of z tends to 0. This is along x-axis we are taking, so this is equal to 1, right? Now along imaginary axis, you know that imaginary axis z is equal to x is 0, so this will be I y. Now this term is approaching to 0 along imaginary axis, therefore the value of f of z will be 0 plus iy divided by 0 minus iy equal to iy divided by minus iy, and that will be minus 1. So f of z equal to z tends to 0 along imaginary axis equal to minus 1. You can see that limit is plus 1, limit is minus 1, limits are different, this is not possible, and therefore this function does not have a limit. Okay friends, now let us see one theorem. This is a very beautiful theorem and important in term in complex analysis. So we see the proof of this theorem. I am going to write the statement of this theorem here. Theorem, suppose that, first suppose that, let us see what we want to show here, what is given here. Suppose that f of z equal to u of x comma y plus I into v of x comma y. This is where and z0 equal to x0 plus iy0, w0 equal to u0 plus iv0. These are the two numbers, and limit of then a limit of f of z equal to w0 when z tends to z0, if and only if I'm writing this short form, if and only if limit of u of x comma y tends to x0 comma y0 equal to u0, and limit of v of x comma y tends to x0 comma y0 equal to v0. This is we want to prove here. So let us start the proof of this proof. We first suppose that let us assume the first suppose limit of u of x comma y equal to u0 and limit of v of x comma y equal to v0, where x comma y tends to x0 comma y0, x comma y tends to x0 comma y0. This is the limit, right? Apply the definition of limit. When we set limit of u of x comma y, whenever that means epsilon delta, for epsilon greater than 0 there exists delta greater than 0 such that mod of u minus u0 is less than epsilon by 2 and mod of v minus v0 is less than epsilon by 2 whenever these are the 2 points. So under root of x minus x0 whole square plus y minus y0 whole square is less than delta. Same criteria by applying the modulus value. What is modulus? Under root of x square plus y square. Here this is from 0, so that will be x minus 0 plus y minus 0 whole square like this. But here the instead of 0 we have 2 points x0 and y0, so I have written this term as x minus x0 plus y minus y0 whole square is less than delta. But friend, we know that under root of x minus x0 whole square plus y minus y0 whole square is equal to, look at this modulus value, x square plus y square, that is mod of z. Mod of z means this is mod of x plus iy, right? The mod of x plus iy under root of x square plus y square. So for this we write here x minus x0 plus I into y minus y0 in modulus, right? This is equal to mod of x plus iy and plus x0 plus minus here minus y0, and this is less than delta. Look at this, this is point z and this is nothing but z0, so that is mod of z minus z0 is less than delta, right? Then here you can see that u of x comma y, u of x instead of u of x comma y I am going we directly write u plus iv minus u0 plus iv0 equal to, this is mod of u minus u0 plus I into v minus v0. This is less than equal to mod of u minus u0 plus mod I is 1. So directly we write this as a mod of v plus v minus v0. Mod I is equal to 1, right? Okay, so here we get mod I, but instead of mod I have directly taken as a 1. But here this is less than epsilon by 2 plus epsilon by 2. This is equal to epsilon. That means here mod of u plus iv minus u0 plus I into v0 is less than epsilon whenever z minus z0 is less than delta. So here this shows that limit of f of z minus z0 is equal to w0. So this is the first part of this theorem. Now prove the second part of this theorem. As we have seen here, let us prove the second part of this theorem. In the second part, we will consider limit of f of z equal to limit of f of z. Let us take limit of f of z. Limit of f of z equal to here limit of f of z equal to w0. Z tends to z0. Now apply the same. F of z minus w0 is less than epsilon whenever z minus z0 is less than delta. As you can see that what is z minus z0 less than delta? Z minus z0 is nothing but under root of x minus x0 whole square plus y minus y0 is whole square. So without we do not like to repeat this part, and we will omit this part and directly write this x z minus z0 is under root. Okay, so here you can see that z mod of z minus z0 is nothing but under root of x minus x0 whole square plus y minus y0 whole square is less than delta. And you can see that u minus u0 is equal to is a less than additional term we write here mod of u minus u0 plus I into v minus v0. We have taken additional term. Okay, so that means single number 2 is less than 2 plus 3, right? We have taken this additional part, and therefore due to this additional part, this part is smaller than this one. But what is this? This is equal to mod of u plus iv minus u0 plus I into v0, right? Okay, so this is nothing but mod of f of z minus w0, and this is nothing is less than epsilon. Similarly, mod of v minus v0 is less than mod of u minus u0 plus I into mod v minus v0. Okay, so this is similarly this is equal to mod of f of z minus w0 is less than epsilon, and whenever under root of x minus x0 whole square plus y minus y0 whole square is less than delta, then what we get here? Mod of u minus u0 is less than epsilon means by definition limit of u equal to u0 and limit of v equal to v0. This is for x comma y tends to x0 comma y0, and limit x comma y tends to x0 comma y0. So whenever limit of f of z equal to w0, when z tends to z0, we have that limit of u equal to u0. So here we have seen what is meant by function, what is meant by limit, and we have calculated limit of a function, then one beautiful theorem regarding the limit. Thank you friend for watching this video.